her work in that space was literally saving lives. Like, no one is benchmarking these data sets. Why do we not have Sunday robotics in every single office, cleaning stuff all the time? So they were also a YC company, and they basically plugged an LLM into a robot.
Hi, Silicon Valley Fellowship community. In this session, there's going to be a talk from Bronte Kolar, co-founder of Zeon Systems. She was very nice hosting us in her office during a batch of the Silicon Valley Fellowship, and like her whole team was there, and she gave an overview about the current robotic landscape. So what's possible, what's science fiction, what is actually working on the labs and in the industry. The real winners between Tesla, physical intelligence, Figure, and all the other robotics company, and also what it actually takes to deliver like those robotic systems from the R&D labs to actual production and to the real world. And basically what she's building is intelligent robotic infrastructure. And of course, she's gonna share what she's building, that is intelligent robotic infrastructure for scientific discovery. And so those like new robotics platform are gonna help thousands of scientists to make like new discoveries to progress society. Okay, let's see. Enjoy.
To actually train their robots, they have a glove that you can see here on the right. And the glove is very similar to the actual glove on the robot. So they can actually do tasks with this glove and transfer it really quickly to the actual hardware. So that's kind of the bet that they're making, is this like interface to train that's very similar to the actual robotic gripper. But I just think they look really cool. You can like customize their hats and stuff like that. So definitely the most friendly looking of all the robots. And kind of another couple of companies, 1X over here, and Tesla. So what they're basically doing is work on generalist models. And the cool thing is that when they fail, they actually have someone who does teleoperations step in to close the gap. So 1X had a really interesting business model where they wanted to be kind of the first humanoid really in homes. And so to do that, they basically launched really quickly, like offered a monthly subscription. And anytime the robot kind of gets out of its distribution, of its training distribution, you can basically have someone teleoperate in and do the task. So this is how they actually like gather more data. They can find out where they don't generalize as well. And it meant that they can get to market faster. But yeah, a little bit of an interesting technique that you can have like a robot like this in your home and someone else can kind of like hop in, control it. But it's also another great way to gather data. And physical intelligence. So they are more of a research lab, but they basically work on a lot of like generalist policies that they make open source, which is really cool. So like Pi 0.5, 0.6, all outputted by their team. Some of like the top researchers in the world are working there. They're really cool. And they kind of made some of the first, not the first, but some of the first open source VLAs, human to robot transfer. They work on reinforcement learning, but they've done like a ton of cool work on, like here's one where they're making coffees. And I think this video goes on for like an hour. So it's just them like autonomously making coffees for a really long time. And that is super difficult to do. Like to basically stay on task for that long of a time is pretty cool. But if it wasn't clear, no one knows what's going on. There's people who are basically like using these handheld manipulators to get data. There's people who are building these generalist policies. There's bets on simulation, and no one really knows who is going to win this market. And this is Boss. So something else to kind of keep in mind when you see these demos is this stuff that you don't see probably didn't work. If something is like cutting all the time, like he was basically like, if I don't see a full like end-to-end non-edited video, I assume something has gone wrong. And so it's why it's really impressive when you see like a Figure or a physical intelligence putting out a video that's like an hour, 2 hours long, and they just like did not edit or cut it. So as you see more of these videos, like keep that in mind, keep Boss in mind at the back of your head, be skeptical. And then data. So many people are talking about like robotic data. I think like we get probably at least one email a week asking like if we need robotic data. We don't, but they still email us. And there's a lot of different theories on where this data is going to come from. So physical intelligence has basically started working on gathering egocentric data. So putting a camera on your head and basically taking videos of humans doing this stuff and transferring those human poses to robot poses and then training on that. And so that's like one really scalable way to get data. Another one is teleoperations. So you'll have people doing like these teleop farms where they're basically like just have desks of people like with setups like this just all day doing tasks and getting data for the robots. And this is really good because you're training on the real hardware. So you're actually like getting data that's not from a hand being transferred to a robot. It is like the actual gripper. And then of course simulations, like this is NVIDIA's bet. Like let's just have these robots running around in sim. And just if we can parallelize that, then we get a ton more training data as well. So this is kind of some of the ongoing kind of places where data is going to come from. But like something to keep in mind is like the data is super important. So whatever you train on it needs to be representative or at least help you generalize the kinds of environments you're actually working in. So like there's a lot of actually debate on how this data scales. So this is like one of the researchers at, we get all of our news from Twitter, I swear. This is one of the researchers from Physical Intelligence, basically saying that like one of the biggest things is like no one is benchmarking these data sets. And you really need to understand like the interplay between quality and diversity of data that you collect and its impact on the policy. So this disconnect between the people who are collecting data and the people who are deploying them kind of breaks that intuition. And so you really want to make sure that Steve's arguing that it's really helpful if you collect your own data. And this is one of the founders of Sunday Robotics. And they're just also emphasizing that in-domain demos, so getting demonstrations of actually like the lab that you're going to be in with the equipment that you're going to use goes 10 times further than if you have like a gazillion videos from like some completely different task somewhere else halfway around the world. So this is also something that's very interesting. And so the deployment gap. So this is like, you've seen all these kind of crazy robot demos. Why do we not have Sunday Robotics in every single office, cleaning stuff all the time? And so I want to show you actually one of our demo videos from May of like what we were doing almost a year ago. And I'm going to tell you why we don't have this in a lab right now. So here's a video of us basically doing serial dilutions. So we're like taking a pipette, we're grabbing tips, and we're basically moving it across the wall plate. And this worked like, at this point we can do this pretty reliably. So, oh, here we go. So then we move to the plate, we find the correct well, and then we pipette. So like pretty straightforward actions. And so what it actually takes to have this usable in a lab is it has to work 99% of the time because scientists are trusting their human samples or whatever samples that they're working with, which are probably quite precious. Errors need to be surfaced. So if something goes wrong, you know exactly what it is so it doesn't happen again. And you still have to maximize hands-off time. So having like a scientist intercept this workflow every 5 minutes isn't going to cut it. And so, okay, like what features do you need to get there? You need being able to localize objects super accurately. You need to make sure that if the arms move, that you can recalibrate them. That it needs to be safe because if someone gets hit by your arm, like you want to avoid that. But also if someone does get hit by your robot, you need tech errors and emissions insurance, which takes a long time to get. You need to test in different lighting conditions. Like we use transparent objects all the time. You need to make sure you manage your cables so someone's not like tripping over. And once again, the errors and emissions insurance becomes very important. You need to have like adequate logging so if something does go wrong, you know what went wrong. And so there's like months and months of problems to solve to go from something is working in your environment to being actually deployed in the real world being used by people. And so this is basically the state that a lot of people are in. And what's even worse is we don't rely on black box models. Our system, the motions, we are like using a pretty deterministic system. If you have a model that you said, do X, Y, Z, and it just runs, like, and it breaks, you have actually like no stack trace of like what was going on and why, or like why it might have failed in that environment, but not in yours. So it's even harder if you have this black box model that's running stuff. Not to say you shouldn't use them, but it just makes bridging this gap 10 times harder. And so you want flexibility, but something we grapple with is like, okay, we want to be like saving the world and have robots everywhere and be automating lab work. But if you're not flexible enough, then you're basically just a consulting company, like putting robot arms and spending like years and years and years closing gaps in use cases that aren't really repeatable. And so it's a balance between trying to get out as soon as you can, but then also not becoming a consulting company. And so it's like the balance that everyone is kind of playing with this deployment gap. So for us, reliability is way more important than generalizability. We don't have a gazillion dollars in funding to basically like wait until the model's 100% reliable. We like have to be in labs now. And so what does this actually kind of look like? Like this scale of hard-coded to like AI everything is, so the first thing is like, if you want to know, okay, like I want to grab this mug with this arm, how do I find out where my mug is in the world? So you could hard code stuff and say, okay, it's at like X90, Y10, Z0, and you just like put it there. And always make sure it's there, don't move it, it'll be there every time, completely hard coded. You could put like a tag, and you could scan, look for the tag, and once you find the tag, then you can use that to basically know exactly where the object is. If you know where the object always is with relationship to that tag. You could also like push things even further and like take a photo of your scene, use a vision model like SAM3 to basically find the object in your scene, and then use the depth information from your camera to like then further place it. So it's like pushing it a little further. And if you're using VLA, then like it actually doesn't really matter because you could just grab the cup from like one line of text regardless. But like the amount of confidence that you can have in this working every single time starts going down as you progress further and further down this line. And so we are always kind of somewhere in the middle of like, how do we kind of get the flexibility, but don't sacrifice completely on the reliability of our systems. And you can also compensate for lack of generalizability by being super flexible in your vertical. So this is like a mouthful, but you can kind of take advantage of, are you working in like industrial settings? Are you in a lab setting? Are you outside? And you can actually use that to kind of take advantage of the things that do change and keep consistent and reliable the things that don't. So for example, for us, like we work with pretty standard equipment. Like everyone uses these tubes everywhere. Like we always find them. The protocols are, usually people make small kind of changes in between them, but they don't change drastically. And then you have compounding effects of if you, for example, learn how to use a centrifuge, and you do that in a flexible way, then every time you see centrifuge, you can generalize. And so we kind of take advantage of a lot of the things that you can kind of like take, like milk almost in the different lab environments. And you can play those to your advantage. And so people find these things in kind of different settings. And that's how you can kind of start being more flexible while making sure that things are still reliable. And so how has AI sped up our team in robotics? So I wanted to tell you guys a little bit, like we are basically all just engineering every single day. And the impact that AI has actually had on our whole workflow has been kind of absolutely insane. So I think like one of the first things is like SAM3 and these like vision models. So like VLM, so for example, with SAM3, you can basically give the name of an object that you're looking for into a photo and get like a near perfect segmentation of it. And so like here's like some examples, but it means that you don't have to do like some mapping or like you have to train your own model in detecting certain kinds of objects and do that for every single object you're looking for. You can literally just ask like Meta's model, okay, like I want to find the red cup, and you have like a perfect segmentation of it. It's obviously like not 100% reliable, but it's pretty good. And then like VLM, so you can ask basically, you take a photo of a scene and you can say, okay, like, is the red cup to the left or to the right of the yellow cup? Like get a response like yes. So for us, it's like you can start looking into different parts of a lab and start asking questions. And you don't have to predict every single one of those questions. So like these tools have been super transformative for us. And also like Claude Code, Cursor. I think, does anyone here have a robotics background or have kind of experience in this space? Okay, yeah, I know you do. Well, there's like an operating system that pretty much everyone has used, like ROS, to orchestrate like all of your sensors, like making sure everything's in sync and observable. And it's a pain to work with, but it's really good. And we actually didn't have to use that for one as a tool because we could build features with Python so quickly. But also our whole simulation stack was able to be like Python based. Here's Annie, actually, our intern. So this has been kind of like, I think Claude is kind of like our honorable 7th employee at this point because it's been honestly incredible. It's not as great at robotics code as like maybe something like if you're building a website, but it's pretty darn good. And yeah, I think kind of finally, like, what does this mean, or second last kind of section, what does this mean for science? So this is really what we care about. Like for us, AI, robotics, all these tools are kind of something that we use to move the pace of this thing that we really, really care about. And so a little bit of background on why robotics was kind of more inaccessible in the past in this area is you have a lot of automation engineers, and they're used to basically coding these like very obscure kind of languages or interfaces. Like this is one of them for Hamilton machines. And so it's super complex. Like if you need a new protocol, you have to enter this really weird interface that only you know, and you have to like program it from scratch. It's expensive. Like up until the last 10 years, like every machine was just like tens of thousands of dollars, like hundreds of thousands for a lot of these larger ones. And rigids, like let's say you have like a full automation stack, and all of a sudden you want to add like a centrifuging step. Like it's just, you gotta start from scratch. And there's no way to interface with a lot of these machines because they're built for humans. So all of these kind of made robotics less accessible in science. And I think for us, like our whole mission and the reason why we care about this is because the impact of slow science is like, these are the people who are responsible for our therapies, for climate change research, for making sure you're not like full of microplastics, for disease not to spread. It's like some of the core parts of humanity, and like making sure humanity does a good job in perpetuity is the work that scientists are doing. And I think a really good example is Jessica, who's one of the scientists that we've worked with. She was the first scientist who actually let us see her lab completely and like show us everything she was working on. She was directly responsible for getting phages. So those are viruses that attack bacteria. She was directly responsible with getting those to patients who were dying of resistant infections. So her work in that space was literally saving lives. And she was brought into Stanford to help build that out. And if you follow her around her lab, a lot of the work she's doing is critical and is like moving the needle in that research. But there's a lot of hours every single day that are like mixing solutions together, like preparing a buffer, putting agar in plates to be ready for like 4 days from now. And so if you look at that time breakdown, it's kind of just expected that scientists do it. But when you have someone whose brain is like literally built for saving lives with this therapy, like why is their time split like that? And how much more could they do if they had that time? So I really think that the impact of not giving people this time back is actually going to slow down the pace that we can do the things that are really, really important. But a lot of this is not new. So to be clear, one of the coolest papers that inspired Tahir and I was Organa. So this is out of the University of Toronto, the Acceleration Consortium. Canada gave their biggest grant ever for this center on accelerating materials discovery and automating everything. And Organa was basically this paper that had a robotic arm doing a lot of these experiments. It's really, really cool. And like some of the first, there was stuff that they were already producing before this, but for us, the moment we saw this, we were like, this is really cool. Like, why is no one else doing this? But people are catching on, and now this is like a very big thing. So in the last 6 months alone, the amount of funding that has gone into robotics, AI, and science, like this weird kind of intersection, has kind of completely exploded, especially in the US. There was this thing called the Genesis mission that was released, where there's like millions of dollars in funding going to some of the largest lab automation companies in the US. The NSF, which right now there's a lot of government funding that's being taken away from scientists. A lot of it is still now funneling to like cloud labs, to these weird new test beds where they want to basically automate centers of research in the US. And then companies are raising really wild rounds. Like Lila, they do lab automation in materials biology, $350 million raise. Periodic labs, they do work in material science, $300 million raise. Like the amount of money, like in my whole life, I've never seen money thrown around like that. And in the last few months, we've been seeing it happen more and more frequently. So people are really, really excited about this space. Here's kind of another example of robotics, AI, kind of intersecting with science. So recently, there was also kind of a collaboration between a biosecurity company, Red Queen Bio, and OpenAI, where they were automating Gibson assembly, which is basically like one part of just like common lab protocol. But it's really cool. They had an LLM controlling this robot arm and actually doing science, which is really neat. and has not been done before. And just finally, to wrap this up, there's some stuff that we kind of throw around on like Slack channels or talk about here that I think is just really weird, random stuff that if you're interested in this space, might be really cool for you to know. So one is Butterbench by Andon Labs. So they were also a YC company, and they basically plugged an LLM into a robot. So they do a lot of work on autonomous organizations. So can you take an agent and have it run a vending machine, like a legitimate business, like you give it money, and you actually see if it could run an organization efficiently. And they also did kind of an experiment where they plugged an LLM into a robot, and they basically measured how well the LLM could carry out basic tasks on this robot. And they kind of measured them together. Turns out they're pretty bad at it right now, and humans are still the best. But like stuff like this is really cool. Like, to what degree can we actually control these robots? Teaching and repeat. So we've kind of thrown around like a lot of AI-based methods. But this is actually one where, similar to kind of Sunday robotics, this one's like a little bit more restricted. But basically, you can demonstrate with a gripper different tasks to do in a lab, and you can immediately carry the same tasks over to a robot arm. So this is like pretty cool, a pretty cool way to get something up and running very quickly in a lab. And last couple, so this is a little bit similar to the last, like taking this arm and gathering data in different settings. So this work, like one of the best papers on this was out of Stanford called Universal Manipulation Interface. And this is basically where they were doing just that. They were taking a gripper, like running around, collecting data with it. So super easy. You don't need this whole teleoperation setup to gather that data. And then they were able to transfer that back to a robot. So this stuff is really cool. And finally, like recently, I think everyone here thought that the Atlas robot from Boston Dynamics was pretty cool. Like, it just looks, I don't know, this recently came out. It was awesome. We were all pretty excited. But yeah, that's everything I have to share with you guys. So like, I know it was a ton of information, huge overview of like a lot of the different companies, some of the work about some of the stuff that we're doing internally. But yeah, please feel free to contact me if you have any questions or want to learn more. Always happy to talk about this stuff. And if you have any more detailed robotics related questions, please talk to Giuseppe, Boss, Blaram, Tahir, Annie. They're awesome, and they could tell you way more about this stuff than I can. So yeah, thank you so much for your time.
I did notice like you guys are using like lab assisted like robots, but like what about like disability, like medicine related stuff?
Oh, interesting. So do you mean for like exoskeleton type work, or?
Yeah, something like if someone has an amputated arm, can you implement your?
I see.
Like something like that.
No, so we are not, just because a lot of the hardware we use is off the shelf. So for a lot of those devices, you need to also like tune the dimensions and everything to a person. And so that definitely involves custom manufacturing. So for us, no, not directly. There is a really cool company that does kind of stuff like this. Tahir, you know, a company that does the bench sitting up, the one that they, so not directly related to exoskeletons or kind of supportive tech in this way, but there's people who are doing really interesting kind of systems on, like, just if you sit down on a chair and you're elderly, like being able to actually have a chair kind of push you up. And so there's like, I think like a whole range of things that you can do there. All of them require just custom manufacturing, which we ourselves don't do. So we don't, but I think it's a really cool space. So, yeah.
Even beyond manufacturing, if you want to build things to people, you need to get FDA approval.
Yeah.
That's like a multi or multi-million-dollar.
Yeah, because like me personally, I used to know a professor at MIT who used to work with like assistive tech long back, and then we were having a discussion with like FDA, and you need a lot of money licensing.
Yeah.
And, yeah.
Yeah, even like the ISO certifications that you need, like it's a long, but I think it's worth, like, it's one of the things that I think is worth doing.
I mean,
And
the
like,
only robotic thing I think that's successful enough in like in terms of like commercially available stuff, is like the Omnibot for diabetes.
Yes, yeah.
Yeah.
No.
Yeah, that's all. I was just
Yeah, I think it's a super cool space. I think the one super annoying thing is just at least from like seeing the stuff that we do, where we aren't even having to manufacture a lot of the hardware, and you still just see like this gap that it takes for commercialization, and it's just unfortunately, like the funding that you need for like FDA approval and all these things. So many things just die before they get to that point. But I think with like a lot of the things that we're seeing, that bridging that gap should be like easier and easier as time goes on. But it's a super cool space.
You guys cater to more like research labs.
Yeah, more research labs. So, yeah.
What's the most complex task it can perform in a lab right now?
For us, it's basically like vortexing, capping, loading into a centrifuge, pipetting, qubit. Yeah, so like basically like some like basic machine tending.
What's the goal?
Sorry?
What's the goal?
So the goal for those are basically across tons of biology workflows. So one of them is, for example, like one is used for quantifying DNA. So if you have DNA samples and you want to basically assess how much DNA is in all of them, all those steps are part of a flow. So we basically we don't have the qubit machine here, but that flow is basically you dispense a certain amount of liquid into every single tube, and you basically load those tubes into a qubit and get the reading. So that flow we've done, and then that is basically for DNA quantification. So finding out how much DNA is in there. Other ones that we're working on are like some cell readouts, like ELISA. We're doing some materials work that we can't talk about as much, but no, yeah, we're basically getting kind of our first set of experimental readouts over the next few months. So right now it's like proving out we've like proven out some of the basic things like tending a smaller set of machines, pipetting, and capping and uncapping, and now we're like putting all those flows together. So with the goal of most experimental flows kind of encompass all those steps, and so we can like nail those, then we can start doing full flows.
From step one to the
Yes, yeah. But basically right now we're at the point where we can do like piecemeal parts of all these different experiments. We're basically like working now on kind of closing those gaps. So yeah, doing our first experiments now, which we're excited about. So yeah.
Oh yeah, thank you for the presentation. It's really exciting work.
Thanks.
Also, I was thinking like, just like NVIDIA is betting on simulation, and maybe Sunday Robotics is betting on imitation learning, or maybe they have some secret sauce. So what are you guys betting on?
Yeah, we're basically betting on a little bit of an in-between. So we don't do model training directly the way that these companies do, but we're basically working on ways internally to build small skills quickly. So those are not as, I get to hear it, how, like those aren't as model-based, but basically we work on ways that you can actually just build very small motions quickly. So a skill like opening a centrifuge or grabbing objects very flexibly. And none of those are model-based. So our goal is if we can basically build up enough of these atomic skills really well, that we can actually start encompassing full workflows. Just because a lot of the things that we see in these scientific protocols are pretty common, and like a lot of the same machines are used. So and we basically have like a variety of ways that we build those individual skills up very quickly. I don't know if you have more to add to.
We're basically betting on classical robotics and chaining together classical robotics with LLMs in the loop, just because I think we fundamentally do not believe that a non-deterministic model is going to work for science experiments, because the requirement, the lowest bar you need to hit is you have a tray of identical tubes in front of you. You need to tell the model pick up tube 6 in row 3, and you need to know how many percent it's going to do exactly that. And at that point, if that's your bar to actually have a useful robot, you basically have AGI. So we cannot have AGI be the lowest bar for this stuff to do.
Yeah.
So in classical robotics, determinism, and then you chain that together with something which is really smart.
Yeah. So for us, we've tested some of these models that they come out. So when Pi drops a model, I remember over the summer we spent a lot of time testing some of these models to see, okay, could we actually use them and bring that into part of our stack? And just for us, the reliability is not there yet. And if we wait for it to be there, we'll like run out of money. So we're basically like this way we can like deliver value really quickly and actually get into labs. But yeah, actually, yeah, we spoke with like physical intelligence, said the same thing to us as well. They were like, don't bank on these models for these tasks like in the next few years. So yeah, still a little ways to go.
And how are you guys like detecting if something goes wrong? How and when do you guys detect? Because that's a critical part for reliability.
Yeah.
We rely very heavily on like simulations. When I say simulations, here it's not unlimited simulations. It's basically a simulated version of the world that we're working in, and we basically place like objects into the world for things that we are working with and track those objects. See on the table, you have 3 items on the table. You can basically build a wall that is just the table and the 3 items that you care about, and make sure you're tracking those 3 items. If you mess up and one of those items is not over or whatever, you know that that's not top. You flag an error or you reset the object.
Is the simulation in like ideal conditions, like at a certain temperature? Like, does it simulate like the real world perfectly?
We don't do temperature, we don't do friction, we don't need any of that. It's more symbolic simulation. So is this object upright? Is this object tilted? Is this object in the hole it needs to be? We don't have to simulate the actual interaction.
Yeah. Yep.
So I feel like if I'm running a long few day experiment, it has like so many like really hard and detailed steps and like only opening like a cap, I don't think that would just like interrupt my flow. So does that make sense?
Yeah, so what ends up happening is the capping was actually for a use case where they actually couldn't, so what we focus on is if you have a shorter, at this period, where if you have a shorter workflow, but you have to do it many, many times. So for example, the uncapping that you saw, that was actually a company coming to us saying, no machine can uncap these tubes. We have thousands of samples a day, and we don't even need to just uncap them. We need to like vortex them. We need to dump out the contents. And our whole automation team cannot do this. And we process like thousands of samples a day. So like this is our bottleneck. So it seems kind of trivial. Like these are like 5 simple actions. But like doing that reliably for like tons and tons of samples, like that's actually valuable for people. For example, these like very long, complicated flows, for us, the technical bar is so much higher to do that. So we are like right now looking at like, what if there's these combinations of steps that are like maybe 15-step protocols, but people have to do them so often, it's their bottleneck. And that's actually kind of like appears quite often. So it's really weird. Like when we heard about this use case, we were like, what? Like that's the thing that's actually blocking your lab. But that's actually what the real world looks like in some of these labs. So yeah. Yeah.
Do you think that your company has fully necessary to be based here in San Francisco to have success, or it could be in another state?
Yeah, I feel very strongly that it needs to be based here. So I lived for a while in the Netherlands. I grew up in Canada, and I've seen a little bit about what those ecosystems are like. And then I was over here for a few years before starting this. And this is like the only place that like the number of other founders that we get to meet in our space every week that come over for lunch, the amount of weird information that you even hear about just because all the companies are based here. So you'll go for lunch and you'll hear about, oh, like this company is working on this or they're taking this bet. Just like that information flow for us is incredible. Even just the meeting people and like the people that we collaborate with. I think there are pockets of the world where you have a lot of universities. So I think that piece is not special here. But so I just think the other companies based here helps us a lot. Like we've tried even like weird hardware. For example, some of our arms we got secondhand from another robotics company nearby. And I think secondly, it's just the risk appetite here. So people here are very willing to try new technologies. They're like, okay, this is a weird robot arm, but this like might be the thing to like actually like this capping use case. They're like, okay, like this could actually solve our problems. And people are so used to seeing weird tech come up and like Waymos running around the streets. And so the open-mindedness of people is really is really exciting here. And so for doing something a little bit kind of newer in the tech front, I think like people adopt stuff like that over here quicker. So, yeah. Cool. All right. Well, thanks so much for your time, guys. If you have any more questions, we're all floating around, so feel free to ask us anything, and feel free to shoot me an email if there's anything that like you didn't get to ask today that you want to know. But yeah, thanks so much for coming by. Thanks.
Thank you.